Now let's look at a new sample, or sorry, example. Probability calculations, overweight men. Recall the use of data from the Centers of Disease Control and Prevention, the CDC, National Health Interview Survey to estimate behaviors such as alcohol consumption, cigarette smoking, and hours of sleep for adults in the United States. In the 2005 to 2007 report, the CDC estimated that 68% of men in the United States are overweight. Suppose we select a random sample of 40 men and find that 58% are overweight. Oh, that was the end of the sentence. Sorry. Okay, let me say that again. Suppose we select a random sample of 40 men and find that only 58% are overweight, even though it's estimated that 68% of men in the United States overall, the population is overweight. If 68% of the US men are overweight, this sample percent is off by 10%. Is this much error surprising? What is the probability that a sample proportion will overestimate, I think that and shouldn't be there, or underestimate the parameter by more than 10%? Let's check normal conditions. Let's see if this is a normal distribution. If it's normal, we can use z-scores to figure this out. Okay, yes, the conditions are met. The number of expected successes and failures in a sample of 40 are at least 10. We expect 68% of the 40 to be overweight. So we'll do n times p. We're going to make sure that's greater than or equal to 10. N, the number of men that we're sampling is 40 times p. The population proportion is 0.68. You get 27. That's definitely greater than or equal to 10. We expect 32% of the 40 to not be overweight, because that's just 100 minus the 68%. Would be that 32. So n times 1 minus p, yeah, it would be 40 times 0.32, and they got 13. That's close to 10, but it's definitely greater than or equal to. So, okay, so we can use the normal model. This allows us to use a z-score to find the probability, and that makes it easier. Let's first find the z-score. Okay, we want the error to be more than 10% in either direction, because that was the question, right? They didn't say off by more than 10%. They just said is off by 10%. That means it could be off by 10% in either direction. The number that we got, or that they described, was 58%. That was off by 10% in the smaller direction because it's 10% less. But the question they were interested in is, well, not just when is it off by more than 10% in the lower direction or the higher direction? They just said 10% off. So it could be 10% to the left, 10% to the right. So we're kind of going to look at the area under the curve on the left and the right here is the idea. Okay. Anyway, just sometimes just translating what they're asking in the question is difficult, just by the phrasing. But yeah, it sounds like 10% off could be either direction. We want the error to be more than 10% in either direction, so the sample proportion could be less than 0.58 or greater than 0.68. Because the population proportion was 0.68, if I subtract 10% or 0.10 or add 0.10. That's what they're saying. Subtract or add. I want to know, when is it smaller than this or larger than this? It does not matter which sample proportion we use to find the z-score because of the symmetry in the distribution. So they're saying, I want to know the area beneath the curve on this light blue portion on the right here, plus the area beneath the curve in the light blue portion on the left. But because this is a perfect normal curve, it's symmetric. That means the area beneath the curve on the left, the light blue, is equal to the area on the right, the light blue. They should be equal. So as long as I find one of them, I'll know both of them, basically. Okay, so we'll do this calculation. I'm going to try to zoom in here so we can see this calculation they're doing. Oops. Okay. So standard error. Okay, they're calculating it just based on that same formula we saw before. Standard area is the square root of p times 1 minus p. P is the population proportion, 0.68, times 1 minus p. We already kind of figured that out above. It's 1 minus 0.68, which is 0.32, divided by n. They're saying the sample size would be 40. If you multiply 0.68 by 0.32, whatever you get from that, divide it by 40, and then take the square root, you get 0.074. Okay, that's our standard error. We're going to stick that in the z formula. That's the denominator. So 0.74 is going to go right there for the denominator. The statistic that was given to us in the very beginning, the problem, they said, that the overall proportion in the US of men who are overweight is 0.68, but the actual statistic they gave us was, well, we took a sample and only 0.58 of them, or 58%, were there. So the statistic is a number that was given in the problem, but different from the population proportion. And the parameter is that population proportion 0.68. Okay, and the numerator 0.58 minus 0.68 would be negative 0.10 divided by that standard error that we found in this first calculation. If you divide those, you get negative 1.35. Okay, that's what we really need. That's what we're going to look up our z-score. If we look that up in a table or we look it up on some applet or a computer, let's see what we get. I'm going to zoom out so I can see better. Okay, open, clear all this, of course. Okay, let's see. Okay, so we want the area in both tails, as it kind of talks about here. So we need to double this area. So you could have either found the area on the left and doubled it, or found the area on the right and doubled it. It doesn't really matter, but the z-score is a negative number. So we found a z-score over here. Yeah. So that's the one there. The area to the left of the z-value is, this is something you would look up in a table or look up on some applet. Don't worry too much about it. You'll be given this in any kind of exam or something like that. The area to the left is this is what we were interested in. The area to the right is the area beneath the curve in this dark blue area, but we didn't want the middle, we wanted the tail. And the area we're interested in was, I want to double that. Yeah, that area on the left will be 2 times that number, the area beneath the curve, 2 times, I shouldn't put an X because that looks like a variable, huh? Or like, yeah, you're solving an equation, 0.0885. So that'll be what we're looking for here. I'm going to scroll down. Let's see. Clear this. Scroll down and see what we get here. Okay. Looks good. So they rounded this 0.0885. I just say it's 0.09. It's about that. Double that. Okay. 0.18. Now our conclusion, finally. After all those calculations, I always forget what I was even doing. Oh my gosh, so many numbers, but I forgot. What was the example even about? If it is true that 68% of US men are overweight, then there is about an 18% chance, because that's the calculation we just found, that the percentage of overweight men in a range, whoops, I need to zoom out here. Or sorry, in a random, see, good thing I zoomed out. I was going to say range. 18% chance that the percentage of overweight men in a random sample is 40 men is off by more than 10%. In other words, there's about an 18% chance that sample proportions will fall below 0.58 or above 0.78 if the true population proportion is really 0.68.